the object with a for in loop, and I assign letter because we're just to be explicit about what we're looking at, because they're going to be individual letters of the string in the string copy object. And now with this tidied up, so if that letter is equal to 1, then it's then just return the letter. But if there aren't any, I put in a return just so there'd be sort of actually there shouldn't be a return. There should be also a console log so you can see it. But actually no, because we're console logging down here. Never mind, I take that back. But yeah, just a way to like, it's like a catch for an error, because it didn't really say what to do in that edge case up here if there are none found.
That's correct. Mm-hmm. Cool. Yeah, I think that will be up to us to decide. So any questions about this code? Does this make sense? What can we clarify further?
Just to clarify, Douglas, the copy is not an actual copy, it's just an object, right?
I mean, it is taking up space. So like what we've traded off, because it's much faster to, well, in this case, we're actually iterating over both. So we're looping over both for at least the length of each one, like of the original string. And then so it's n of and m, which is also however many letters, because there might be fewer if there are duplicates.
Yeah, we'll think about that right after.
Yeah.
But to answer Joanne's question, no, it's not really a copy. It's just an object that keeps track of the count like this. Cool. So now let's talk about the time complexity. What do you think? Actually, let's do this on the chat. Type in the time complexity and don't hit enter yet. Let's give like a minute to type in the time complexity, but don't hit enter yet. Whatever you think the time complexity of this is.
Hit shift. I thought that was going to give me. Sorry about that.
Okay. We have one early answer, but just give me a thumbs up if you have typed something in the box. Okay, thank you, Joanne, Suzette, Kathy, Brianni, Giselle, Jonathan, Sergio, and Khadija. Type in the text box in the chat. Okay, Sergio, and Khadija. Well, so let's just.
You want me to type it or say it?
Yeah.
Say it? Oh, I put linear.
No. Just like put it on the chat, but don't hit enter yet. We're gonna hit enter. Okay. So everyone ready to hit enter? Let's hit enter on the count of 3. 1, 2, 3. And linear. So can anyone say why is linear and what is n?
I choose O or N because depending on the length of the string will depend on how long this function runs.
Yeah. Give me an example.
Well, if we have in Doug's case on line 36, if we just put A, B, C, D, E, A, B, C, D, and O, it would just go until the end of it. But the string can be infinitely long as well. So we can either have 20 characters, 56, or even 1,000,000.
Yeah, I think in here we can think of it like in 2 ways. One is like the amount of time that it's going to take. So if we think about like if we think about like going through a string of 10 characters taking 10 milliseconds, if we go through a string of 100 characters, it's gonna take 1,000 milliseconds. Is it 1,000? Yeah, 10 times 100. And yeah, and the other way in which we can think of time complexity is like the number of operations, and not so much about the specific sort of time, but the number of operations that's being done. And does anyone want to add anything to that? Yeah, that was.
In this case, I think n would be the length of the original string.
That's correct. Yes, thank you for adding that. Yeah, you always want to say what is n. What specifically is n? Cool. Okay, so open the chat again, and now, if you don't know, guess what is the space complexity of this algorithm. So if time complexity is the rate at which the algorithm, the time the algorithm takes to run grows based on the input size or the input length, space complexity is the rate at which the space that the algorithm is taking on grows as the input size grows. So if you're not sure, just try a wild guess, and that's the point. We'll learn. So give me a thumbs up once everyone has it typed in the chat box. Don't hit enter until I count to 3. Okay, I see 3 thumbs up. 4, 5. I think I'm missing Kathy, Giselle, and Khadija.
Can you
Yep.
can you repeat the question?
Yeah, guess or if you have an intuition about what the space complexity for this solution is.
I can't find my reactions when I'm screen sharing, but I'm giving a thumbs up now.
Cool. Yeah, I can see you. I can see you if you do a physical thumbs up. That works too. Okay. I think. Okay. So on the count of 3, hit enter. So 1, 2, 3. Okay. Cool. Okay, we have n, log n, Jonathan. Mostly we have n's, log n, Jonathan, constant Joanne, Sergio, n2, linear. Okay. Let's go. I guess, Jonathan, what do you think is log n? Oh, I think we can hear you.
I believe when Ben was telling us about space complexity, log n would be, I think, how much space was needed based on the size of what was needed.
Yeah.
Maybe I'm explaining it wrong.
I guess we'll get to it. Though this wouldn't be log n specifically. Now, Joanne, what do you think is of 1? 1 constant.
I think it's because of the input size. I don't think we're adding anything, so to speak.
Okay. So you're actually, so not that we're not, I think your explanation is not correct, but your answer is correct. This is constant time, constant space, and we're gonna talk about it. So yeah, mostly you will think of n. Well, also actually I want to hear from the people that said O of n linear. Why do you think is O of n linear? Giselle.
So I thought it was O of n simply because the size of the object that we're creating depends on the length of that string. I was thinking it could be constant in that, like, if we use strings and there's only letters in them, there's only 26 letters, so it's only so many keys that can be created. But again, the object grows as we begin to add all those keys in and we loop through it. So that's why I figured that it would be dependent on the size of that string.
Mhm. Give me a thumbs up what Giselle said made sense. Cool, thank you. Yes, that was very good, very well said. Yeah, you could think of it like, let's think about, and this is why it's important in whiteboarding and when you're in an interview specifically, think about the worst case and the best case. So let's think about like, what would be the best case for this algorithm? What input size will be like this best case or the smallest case?
O of n.
No, but in terms of the input size, what will be like the easiest and simplest input that you could get? Yeah, Douglas.
With it still finding a unique letter?
Yeah,
It's either 2 or 1, but I think it might be 1 if there's only one letter in the
Mhm.
like if we get an input of 1 letter, then that's unique and it would trigger it.
That's correct. Right. So that's the simplest case. Like the best case is if we have a string of only one letter. Our loop will run one iteration, and we'll have our answer. What about the worst case? What is the worst case? The worst possible case?
An infinitely long string.
But say more about the infinitely long string. Yeah, but I think something related to what Giselle said at the end. Anybody else? Douglas.
It would be a long string, but where every letter is unique. So that way we're pushing everything into our new object and building an object that's as long as our string.
That's correct. And how, if we say we're focusing on the letters of the English alphabet, how many letters is that?
Oh, you're right. I'm sorry. That's that's correct. 26 could be, I guess, the worst possible scenario.
26, right? So if we have a string that has 26 letters and all of them are unique, even if they repeat like 1,000 times, that will be the worst case. Now let's think about then how does our object have like a maximum number of keys that it will ever have, no matter how long the string is?
So it can only have as many letters as there are in the alphabet. So depending on what alphabet you're using or if you're using anything else. But say we're, for argument's sake, we're only using the English alphabet and only lowercase letters. It can only be those 26 letters that can be keys in this object in string copy. So the largest size that string copy can be is 26 keys. It will always be that amount, and that's why it would be constant time as opposed to linear.
That's correct. Absolutely. Any questions or thoughts on that? So for space complexity, you want to look at variables that you have created, and you want to look at how are those variables growing with respect to your input size. Initially, and this was my thought when I was learning as well, like, oh, this is linear because, as if the string is longer, then we're gonna end up adding more and more keys to the object. And the object will grow as the length of the string grows in a linear fashion. But then there's that sort of side thing about, well, the English alphabet only has 26 letters. Let's say the English alphabet, and I didn't specify here. Let's say you were only focusing on letters, not symbols or special characters. So our object is capped at 26 letters, as Giselle explained earlier. And even I was thinking that even if we had like all the letters of all the languages, that's still a finite number. That is not infinite. So it will still have a cap, I guess. Yeah. Okay. Other thoughts, questions regarding this question in particular? So we then found out that the time complexity is linear. Oh, also, I guess on time complexity, we can talk about the first loop being linear. Why is it linear? Because it has to visit every single character in the string, and for every single one, it has to be added to the object. So you could say that this here is of n, right? How about this here? What is the second loop of what?
Oh, one.
Of one, that's correct. Why of one?
Because the input size is not growing, we're just returning one thing.
Nope. Other thoughts? This is all one. It is because of the same reason of the 26 letters of the alphabet. At most, how many times would this loop run? Maybe Joanne?
26.
26 times, right? 26 times. And yeah, cool. So that's 26 times. It doesn't matter how big, if we have a billion elements, they will still be just 26 times. We can consider that a constant. So if we were doing like this, it will be like O of n plus 26 iterations, where n is the length of the string, but we drop the constants like 26, and we just say time complexity is all. Space complexity, we said constant. Cool. Okay, let's move on to the second exercise. Does anyone want to share the solution for the second exercise? And let's talk about the time and the space complexity. I think maybe Brianni or Khadija can share that.
I could do that. Hold on.
Like, give me a thumbs up if you got to this exercise and got a working solution.
Can you see my screen?
Yep.
Okay. So
Could you add a little bit of zoom? Just so that we can see the writing a bit bigger. Yeah. Yeah, walk us through.
okay. So for this problem, I created a empty object. So for the first loop, I loop through the array. If the okay.
Or actually, could you explain the problem first? Like, what is it that we have to do for this?
Oh, so for the problem, we got to take in an array and find the one that doesn't have a pair. So basically like the first one, but with numbers, I guess.
Got it.
So I created an empty object and then I'll loop through the array. So if the element doesn't exist in the object, then I will add it. And then if it does, then I would just add one to the value. And then for the second loop, I will loop through the object. And then I just said, if that element mod 2 is equal to 1, then return the key in the object. So it would just check to make sure it's not the value is not even. So for that one, I got 6, which was the output.
Okay.
The time complexity is linear, and I'm not sure about the space complexity.
So anyone wants to say why is it linear time in time complexity? And like, it might sound like stating the obvious, but we should do it, and you should do it in a whiteboard in view. Even if it seems like obvious, say, why is it linear time?
Because of the length of the array.
Can be a little bit more detail.
Depending on how big the array is and how many elements we have in an array will depend on how many times this function runs. I mean, or that block of code runs.
That's correct. The block inside of the for loop will run as many times as the length of the array. That's correct. Cool. How about the second loop? What's the time complexity of the second loop? And here, I guess, like, let's also think about what is the best case, or what is the easiest case, and what is the worst case. So what is the simplest case for this problem?
Just having 3 elements?
Just having 3 elements,
Or, yeah.
or having 2 elements, or having also 1 element, right? So a small input. So if we have 3 elements, let's say we have one. Let me see. So we have 1, 2, and 1. We know that, you know, the length is 3, so I'm going to say n. Oh, that's n. N is equal to 3. N is the length of the array, right? So we know that this loop will run 3 times. How many times will this loop run for n3?
3 times, right?
It'll run 2 times.
2 times. Because this first loop, what it does is it creates an object with value 1 and a count of 2 at the end, and a key 2 and a value of 1. Basically just keeping the count. So how many keys does our object end up with? It ends up with 2 keys. This loop will only run 2 times. Okay. How about the worst possible case?
If the array's length is, I guess, bigger or not.
Mm-hmm.
Yeah.
Okay. Anybody else wants to take a shot on that? I guess I didn't specify in here. Oh, like that you're guaranteed that there will be 1 element that doesn't have a pair. Right? So in other words, you're guaranteed that all elements have a pair but 1. So I guess we can talk a little bit of n a little bit here. So in time complexity, we already saw that, well, here, we can already see that even in this example, for this second loop will always run less times than the first loop. Right? That is thinking if we have the worst case where we have all unique numbers, let's say, even though the question I just said that you will have pairs except for one. But let's say you have all unique numbers, then the first loop will run n times. It will run as many numbers as you have, and the second loop will also run n times because you end up with an object that has all unique numbers. So in that case, both will be, let's say, n. The total will be just O of n in terms of time complexity. If we think about all the numbers have a pair except for one, here, let's say all the numbers have a pair except for one. If I have an array of 100 elements, and I'm guaranteed that all the elements have a pair except one, how many times will this loop run? Or in other words, like how many keys does my object end up with?
There'll be 99 keys if it's 100, and each of them should have a value of 2.
99. Who agrees on why and who disagrees on why?
Well, is it 1 to 100 or just?
So let's say I have 100 numbers, and I'm guaranteed that for each number there is a pair in there, but for one, there's one element that doesn't have a pair. Suzette.
Would it be like 49?
49, exactly.
Okay, 49 and 2 values.
If they have pairs, it means that there's doubles except for one.
That's correct. So you end up with this being this loop running 49 times. Yeah. Okay. What if we have 200?
That would be the case where there's like 99.
That's correct. Okay. What about 1000?
Would it be 499?
That's correct, right? Okay, so we can say, okay, so the second loop will basically run, if this one runs n times, the second loop will roughly run n times divided by 2, because we're guaranteed that each number has a pair. We'll roughly run n times divided by 2. And if we will do like, this will be O of n plus O of n divided by 2. And this is like the total runtime. But in here is like this O of n, this is not a constant, still depending on n, but it's less than n. Half n is less than n, so we just say this is O of n. In that. And this is true, like actually this is the same for the space complexity. This loop will run 49 times if we have 100 elements. So it will run roughly half n. And this is so we end up with this time complexity of O of n total. For space complexity, it's the same thing because not only, so the number of operations is half n, and the number of keys that are being created in the object is also half n. So the space complexity for this will be O of n in space complexity. So we talked about this is time complexity O of n. space complexity is equal to O of n. So it just happens that in this algorithm, like the time and space complexity is the same, the number of operations and the number of keys that we end up with. And you could say, you could say, okay, this object will end up with half n keys, where n is the length of the array. If we do like, if we say that is the time, that is the space complexity of n here, that's the space complexity. We know that object will have at most half the length or half the number of, it will have half the number of elements in the array as keys. So half n basically. And here we drop the constants. What is the constant here? Just divided by 2. We just say O of n. So in big O notation, you drop the constant. So here, and we drop the non-dominant terms. In this case, like when we have these two, these both are n, but the big, we sort of, you can think of it as we stay with the bigger n, basically. And we can drop the other one. Okay, and one interesting case about this is that the space is O of n. How come the space complexity of this is O of n, where the previous one was constant, even though we're sort of doing the same thing.
Can you repeat your question again?
Absolutely. So this question and the first question are very similar. We're keeping track of like a counter of how many elements we have seen. In the previous one, what was the space complexity on the first problem?
It was constant.
It was constant. And why was it constant? Or anybody else?
Was it because we had a fixed number of letters in the alphabet?
Mm-hmm. That's correct. We have a fixed number of letters in the alphabet. So it doesn't matter how big our array or how big our string is. We will only use at most 26 keys in the object, right? Now, how does that compare to this case, this example?
We have an infinite number of numbers.
We can have an infinite number of numbers. That's correct. That is correct. Does that make sense? Maybe not. Let me know. Like, can I re-explain anything? So here, like, as we discussed just one more time, the object will end up having as many keys as the length of the array divided by 2. Right? And this was one of the sort of toughest things for me to grasp. Like, is all of n divided by 2, like half n is better than n. It's definitely better than n. It's half n. But for big O notation, that doesn't matter because it's all about the growth, the growth rate. And we saw here that if we have 100, then the number of keys is is 49. If we have 200 is 99. If we have 1,000 is 499. Like the rate of growth is linear, basically. It doesn't matter if it's growing by half. It matters that it's growing linearly with respect to the input size, and so on. Questions or thoughts on this specific example?
Is it n divided by 2, or is it n divided by 2 minus 1 in this case?
Could you repeat the first part?
Sorry, I was just wondering, is it n divided by 2, or is it n divided by 2 minus 1? Because we still need one that doesn't have a pair in this case.
That's correct. Yeah, yeah. It will be n divided by 2 minus 1. Yeah, but again, that will count as like if we do of n divided by 2 minus 1. Remember that, yes, that will be like, if we want to be super accurate, that will be, but we drop the constant terms like the 2 and the minus 1. And we just say is all n. Cool. Other questions or thoughts? So what was the time complexity again?
Oh, man.
And the space complexity.
O of n divided by 2 minus 1.
Okay, but remember that in big O notation, we drop the constants, like the divided by 2 and the minus 1, and we'll just say O of n.
All right. Okay.
Cool. Okay, did anyone do the third problem?
I started it while we were working on the last one, but it kept making my Zoom crash, so I stopped.
Cool, but
And thank you for letting me back in. I apologize for crashing over and over again.
no worries. But I want to see anybody else if they got to that question. Question number 3. Nobody got to that up to that one.
I mean, we started working on it. That's the one. Hold on. That's the one with
The second smallest in the array?
Yeah.
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 So I think you guys had answered that for one of the, I think it might have been like Unit 1 assessment. But anyone want to like describe the high level approach? How that will work?
For that one, that's when I would have 2 variables. I would assign both of those variables to the first element of the array.
And then, so let's do it here.
I mean, I can send what we did.
Oh yeah, sure.
Yeah, my computer.
Do you want to share your screen? Because if you share it here in this chat,
You won't see it?
when I copy it, it doesn't let me copy well.
Okay. Give me a second. Let me put her on that one. Sorry, give me a second. We're just working together with Khadija, Brianni, and them. Yeah. And second smallest. I'll share my screen now. Can you guys see my screen? I can't see myself. Alejo, you're muted. I can't hear you.
We can see your screen.
Okay, yeah. So this is kind of the approach we had. So find the second smallest element in the array, and with that, we assigned, we created two variables and assigned them both to the first element of the array. And then we started to loop through the array.
Mhm.
And as we looped, I mean, we didn't finish it, but as we looped, we put that element like array at I in its own variable, and we were comparing it to the variables we had prior for smallest and second smallest. So if current is smaller than the smallest, make current the smallest and make the second smallest smallest.
Mhm.
But while we were doing that, we came across
Oh,
like there was a bug because we're not done. We need like
so you're really close. Does
so
anybody see that here? Or yeah, go ahead, Suzette.
no, I was thinking of adding like other if statements, so like checking for the array length. So if it's like 1, just return that one element and things like that. But I know there's another bug.
Yeah, I think that wouldn't be necessary because even if the array length is 1, oh, if the array length is 1, yeah, I guess like that's sort of an edge case. Like, what should we return? Maybe just the one element or undefined. But I think since we're talking about like time and space complexity, let's not worry about that one. But does anyone see here like where the problem might be? So, Suzette, could you walk me again from line, like what line 7 to line 9 is doing?
So here,
Mhm.
we're as we loop through the array, we're checking to see if current, which is array at I, is smaller than the smallest, which is array at 0.
Okay, and if it is, what do you want to do?
Replace smallest with the value of current.
Okay, I don't think that's what you're doing on line 8.
Oops. Is the other way around? Smallest equals current?
Yep.
See, this always gets me. And then this is right? Second smallest.
The thing was that you will want that to happen before you set the current to the smallest.
Oh, okay.
So yeah.
Oops. Okay, whatever.
Okay, let's try this with the example.
Hold on, give me one sec. Oops. Where is it? This.
Line 37. No, should line 29.
29. Then, oh my God. Okay. Console log. Mm, it worked.
Cool. Okay, any thoughts or questions on this? Okay, so in the chat, type in the time complexity. Don't submit it yet. Just type in the time complexity and submit on the count of 3 and give me a thumbs up once you have entered the text and is ready to hit enter. Okay, I see 1 thumbs up. 2, 3, 4. Joanne, Douglas, Giselle, and Khadija are missing. Okay, Joanne.
I put mine up. You don't see it? I don't know what I'm doing wrong.
Oh, maybe, I think maybe
Like
it's in the reactions,
huh?
In the reactions icon at the bottom of Zoom.
Oh.
That thumbs up.
Oh, this one. Okay.
Yeah, there's another one in the participants tab, yeah. Cool, so on the count of 3, hit enter. 1, 2, 3. Cool. Linear time. Kathy, I'm gonna pick someone at random. Kathy, can you explain to us why is it of n or linear time?
Well, you are iterating through the length of the array. I don't know how to explain.
That's fine. And how many times would we iterate them?
Based on the length.
Mm-hmm. And so if we have 100 elements, how many times do we iterate?
100 times.
That's correct. Cool. Okay, great. Now, if you are unsure, just try to guess. What is the space complexity? Don't hit enter yet. Enter it. Put it in the chat, but don't hit enter yet. Just type in the time complexity, the space complexity, sorry, space complexity, and we'll submit in the count of 3. Space complexity for this algorithm, and gives me, before you hit enter to submit, give me a thumbs up once you have it typed. Okay, I see most of you, Suzette, Khadija, missing. If you're not sure, just guess.
Wait, can you guys see like my chat box?
No, we can't.
Okay, but
Yeah, Zoom hides its own windows on your sharing screen. Okay, 1, 2, 3. Okay. So we have a variation. We have constant and linear. Anyone that said constant want to speak about why? Douglas.
Is it because at most there will only ever be 3 variables filled, like 3 elements, or
what are those 3?
One, it would be smallest, second smallest, and current, taking up space, but they're only just one thing.
That's correct, and that thing is not growing at any rate based on the size of the input. So this is constant time, constant space. It doesn't matter if the array is 1,000 elements. This will just use those 3 variables, and none of those 3 variables are growing as the input size grows. So it will be 3 variables with 3 elements. If it's one, even if it's one array with 1 element, and the same if it's 2 elements, 100 elements, 1 billion elements. The space that this algorithm is occupying is constant. It's not growing in any way or fashion regarding the input size. Cool. Questions or thoughts on that from maybe the people that said linear or O of n? So this is like, I remember, I feel the same, the way you feel, where I remember I sort of understood time complexity, but space complexity didn't really click until later. But it was about just sort of realizing that they're the same thing. Like, you're about measuring growth rate of time or space and how that relates to the input size, the input length, how many elements you have, basically. One is just occupied about the time, and time in, I like to, more than time specifically, like milliseconds, seconds, the number of operations. And the other one in space being occupied. Arrays growing, linked list growing, or stack growing, which we're gonna get to see an example of. Okay, let's take a 5-minute break to 9:10. Let's then come back for 2 more, and we'll be all set. Don't leave the room, just turn off your camera. Be back in 5 minutes. Okay. Let's let's reconvene. Let's see. Give me a thumbs up if you're back with us. Cool. Let me figure something there. Cool. Okay, so I'm gonna share my screen in here for this one. Cool. So we have this problem where we want to find all even positive numbers in an array. We receive an array like this: 1, 2, 3, 6, 8.
I think we're on your Slack channel, not your
Oh, all right.
not the code. That's okay.
Cool. Here. Now you can see the code, I guess. Cool. You see the code? The code?
Yep. It's sorry. I
Right.
can see it. Thank you.
Cool. Okay, so we have this function find even that will basically return to you all even positive numbers in the array. So if we get this array 1, 2, 3, 6, 8, we should get 2, 6, and 8 because those are only the even numbers. Now let's talk about have your chat ready to go. Put in the time complexity you think this is, and let's submit on the count of 3. Give me a thumbs up once you have stuff in your box. Cool. I have 5, 6, 7, 8. Catherine and Khadija. Okay, on the count of 3, hit enter to submit. 1, 2, 3. Oh, and I have to find the chat because since I'm sharing the screen now. Okay, linear time. Everyone got this one. That's great. Anyone wants to say why is it linear time?
Because it'll have to loop over the input at the very least, and in every scenario, it'll have to at least iterate for, and n would be the length of that array.
Mm-hmm. So how many times would it iterate?
5 times for the sake of the input there.
Mm-hmm. Or n times for general speaking, right? Cool. Does this make sense here?
Yeah, it does. We're using an array method to filter through the array. And the condition is if the array at index num is equal to 0, when you modulo by 2, then we're returning the array with those values. But since we're using array.filter, it's a copy of the array because it's we mutated it.
We don't mutate it. We return a new array. But yeah, this here is correct. I wouldn't say the index num. This is the actual number. So this is basically saying if we go just a quick sort of refresher on filter. Filter takes in a callback function. This is what this is. Is just that I wrote it in one line. This is a callback function, an anonymous function that filter will pass in the current element that is iterating over. In this case, I call that element num. And the rule for that callback function is that it must return a Boolean. The callback itself must return a Boolean. For the elements for which the callback returns true, those elements will be kept. For the elements for which the callback returns false, those elements will be left out and not in the final result array. So this function basically, as Jonathan says, it will divide the number modulo 2, and if the result of that modulo is 0, we know that it's an even number. So this expression will return true or false for each number. For those that it returns true, it keeps. For the ones that it returns false, it moves on. Cool. Okay, so that's the filter. I wanted to make sure that that makes sense. Filter is something that I was glad to see that all of you say linear time. That's, you know that the filter is a loop under the hood. That's really good. Most array methods are a loop under the hood. Not all of them, but most, and so on. Okay, now, so we have the time complexity. How about the space complexity? Anything growing here in terms of space? Let's do the same actually. Have your guess ready to go on the chat. Give me a thumbs up once you have that, and let's submit on the count of 3. Let's take a minute for maybe people that are undecisive. Okay, I think I got most. I'm waiting for two more people. Okay, one more. Gotcha. Cool. Okay. So for space complexity, on the count of 3, hit enter. 1, 2, 3. Okay, cool. So we have some variation here, which is good. It's good for discussion. Some people say constant of 1. Brianna and Sergio say linear of n. Jonathan, wait, actually I don't, oh, this is weird. The time in the chat box, it used to have the time so that I could see which answers were from the previous question. So I think that's, yeah, I guess I don't really know now.
You have to put your mouse over and then you could see the time.
Oh, thank you. Wow, that's interesting. A piece of user experience there. Cool, yeah. So we have of n and constant. Anyone wants to make an argument for either of them?
I say O or N because the array is growing based on the filter.
Say more about that.
If we had all odd numbers, then the array would never grow. But since we have even numbers,
if we have even numbers, the array will never grow. What array?
I mean not array. We put even. Let even, right? Which is basically a copy of the array. And since we're returning even numbers, the even array will grow based on how many even numbers that we had in the filter of the original array.
Mm-hmm.
So if we only had one even number, then only one thing would be an array. One thing would be in the even array, but if we had multiple even numbers, then we would have n number of even numbers that's in the array when we filter it.
Yeah, I think you were gonna go. I think what you were trying to describe was the worst case. What's the worst case for this?
0.
That will be 0 or 1 element will be the easiest case. What will be the worst case that you said it at the beginning, where all the numbers. And I guess I should say that the worst case in terms of space complexity. actually the same for time as well. But you said it at the beginning, if all the elements are what?
Odd. Then we wouldn't return anything, right?
Okay, so in terms of space, when all the elements are odd, we have the best case in terms of space,
Right.
because even will be length 0 will be empty. But what happens if the arrays, all numbers are even? How long will it be even? How long will even be?
The n length?
No, that's correct. It will be n, where n is the length of the array. So actually, that was a good exercise in terms of space complexity. The best case is when all the numbers are odd, and basically even ends up empty. Even is an array that we're creating that will be the result of the filter, right? And in terms of space complexity, the best case where we don't use any extra space is if all the numbers in the array are odd. Now, the worst case is if all the elements in the array are even, right? If all the elements in the array are even, we end up having the even array be as long as the original array, right? So, and also time and space complexity are all about like the worst case, basically. What is the worst case? So we were able to identify for space complexity is constant time if the space complexity is constant time. Space complexity is constant if all the elements are odd and we have no even elements. But in the worst case, which we're mostly interested in, if all the elements are even, then the even array ends up being as long as the original array. And here we have this even variable, even array that will grow depending on, it will grow linearly with respect of how many elements are even in the array. Questions, thoughts about this one? So here I had it here in regular. If the filter is a bit complicated, this is why we could do it like without the filter basically, or in other words, this is basically what the filter is doing under the hood. We have an even array that starts empty. We look for num of array. If that num divided by 2, the remainder is 0, then we push num onto even, and so on. So don't let yourself, I guess, like get tripped off by the fact that you're using array methods. Whenever you're using array methods and you don't think that you can figure out the time complexity, think about how would I implement it if I didn't have that array method, basically. And if necessary, write it down, and then you can work with that a bit more easily. Yeah, and then here we can see that even will start empty, but it will grow depending on how many numbers. It will grow linearly with respect to how many even numbers there are in the array. And we discussed what the worst. So just to reiterate and contrast, for the best case in space complexity, where all the numbers are odd, and we end up with nothing in even, that's the best case for space, and it will be constant. Now, in terms of time, this is linear time, regardless of whether all the elements are odd, or all the elements are even, or all the elements are mixed up. Because we still have to iterate, we still have to visit, we still have to go over every single element in the array. So our loop will run n times, where n is the length of the array. So that's sort of a contrasting on like time and space complexity. Time, there is no best case. You will always go all the way to the end, visiting all the elements, comparing all the elements. But in terms of space, there is a best case and a worst case. Cool. Any final questions or thoughts about this example?
Not necessarily about space or time, but vocabulary. Quick question: when you don't need to put what you're passing through before a fat arrow in parentheses,
Uh-huh.
that's an implicit return.
Oh, you mean this parenthesis that I just added?
Yeah. When you don't need them.
Yeah, so that wouldn't be implicit return. You don't need them when you're only going to use one argument from the callback.
Oh, okay.
Filter also receives the index, so here we could get an index. And if I want to use more than 2 arguments, I will need the parentheses.
Gotcha.
However, now that you mentioned implicit return, this has an implicit return. You see that I never say return here.
Mm.
And I'm not using curly brackets around here. This is an implicit return because I'm not using curly brackets and I'm not using the return keyword. If I want an explicit return, what I will need to do is say this. Oops. Like that. And then break it down into multiple lines and so on. Cool?
Thank you.
Yep. Other questions or thoughts in general?
So in general, when you're stating the, what is it, space complexity, do you, or like in general, like any kind of O big O notation, do you always state the worst time or like the worst case scenario, or do you always state like the best case and worst case? Like what is the official, this is the time complexity? Because I'm assuming it's the worst case scenario, right?
It's the worst case scenario. I think it makes you look good if you're able to identify the worst and the best. But for sure, the worst. The worst is much more important than the best. But like, I guess, if you can stay the best, that also tells that you know what you're talking about. You know exactly how your code will behave, and are able to identify what the best case will be. But if anything, the worst, always the worst. That's a good question. And that applies for both time and space. Like developers, most of the time, always assume the worst. Because yeah, I was thinking about, I guess, like, just on a side note of that, I was thinking about my nephew. He's an aircraft technician, and he used to work for Delta. Now he's unemployed actually, and now he was working for like a contractor of Delta. But anyway, he gets like very cheap tickets to anywhere he wants to go. And I was thinking, I would love to work for an airline to do the same thing. The thing is, airlines, they don't seem to hire junior. And I was thinking, like, why is that? And I guess, what it came to mind is like, well, if you make a mistake or a bug in an airplane, that's lives that could, that's a lot of responsibility, and those systems need to work. So that's what I thought. I don't really know if that's really true. I guess they also have some other systems, but I thought that was interesting when I was looking for jobs in airlines. They were always looking for senior people. Okay, so let's move on to this one, and I think we're gonna see this one, pair numbers, and then the recursive sum, just to see a recursive example. So let me give you like 5 minutes. Think about how you would do this problem. Can you guys hear that?
A little bit, but
This is my terminal making noises. So any ideas or thoughts? Yes, Douglas.
So my first idea would be to make a copy of the input in pseudocode. Then I would put into a variable the length of the array, and then start looping over my copy of the array. And we're going to make a recursive function, and that recursive function would so make up as like pairs using the first element of the like make as many pairs with the first element as it can. For example, for the second input example, 1 is able to pair with 2 and 3, and then it's at the end of the array. And when it can't make any more pairs, you unshift. No, I'm sorry. You shift, pop, push. Yeah. It's like you knock the first one off, put it at the end, and then loop again. But decrement the variable that you have holding the length of the array until, and that's your base case. So when your counter is at 0, your looping is done. You've made as many pairs as you can.
Yeah, I kind of think that will work. I didn't think about the recursive approach for this, but I actually would like to leave the recursive for the last example.
Oh, okay, cool.
Any other ideas? How can we make all possible pairs? This can be like an algorithm, kind of like to pair people up each day. We imagine you have like 2 seats, and each day you want them to not only switch seats but also switch pair. Any ideas how we can do that? No other ideas? So what is it that we want to return here?
Looks like we need to return as many arrays of 2 elements as we can make given an input.
That's correct. As many pairs as we can make. And an element cannot be paired with itself. So other ideas for how to accomplish that?
I'm not sure if this is gonna work,
Go,
but
go ahead.
I was thinking of possibly like nested loop. I don't know. Well,
Yeah, say more about that. That's the right way.
um, just to basically keep track of the numbers. So if you start with the first loop and it starts at 1 at the first element in the array, and then the other loop will start at the second element in the array, just to like check. So every time it moves, the second one moves. Just pair them up.
Oh, I see. I think what you mean is that I equals 0 as less than the other length. Actually, that just made me. I was reviewing this book before we came in, looking for an interview, and there's one example here. That actually left a marker on. So we can take a look. Let's take a look at this one first, and then we can take a look at this one, which is the exact. It's the same, just with a slight variation. That we can take a look at. So yeah, okay. Let me take a little bit more of a drive here so that we might be able to finish earlier. Let's say we have let A of array. So we're gonna have A right here. Let's do A, it can be A, let's do X also. X of array, to pick any variable, but X will be the number. And for each number, so what we're gonna do is, for each number, where is the zoom? So we pick each number and we pair it with the other two, right? And so that will give us 1 and 2, 1 and 3. After that, we will pick the second number. We pick the second number and we pair that one with the other two, which is with 1 and 2. That will give us 2 and 1, 2 and 3, and so on, basically. We go on to the other number and we pair it with 1 and with 2, which will give us 3 and 1, 3 and 2. And that should be what we have. We have 1, 2, 3, 4, 5, 6 pairs. 1, 2, 3, 4, 5, 6. Cool. So the way in which we will do that is we just do let X. Oh, I'm still in drawing mode. Let's let X for the first number. Yeah, actually, let's do this num1. And I'm gonna say I'm gonna loop again for let num2 of the same array. We have this clause here that all numbers are unique and numbers cannot be paired with itself. So what we're gonna do is if num1 is not equal to num2, I want to pair them up. We will pair them up, and for that, actually, let's keep a variable here, const pairs, with an empty array. What did I do? And what we do is, if the numbers are not itself is not the same number, so we don't pair 1 with 1 and 2 with 2, what we want to do is let's push onto pairs. Let's do pairs that push, and let's push in an array with the pair with num1 comma num2. At the end, let's just return pairs. And let's try this out. Let's do console log their numbers with 1 and 2. Repeat that with 1, 2, and 3. Does anyone see the error? Why this is green right here? Oh, I'm using a parenthesis. Okay. Let me erase this. Let's try this out. I don't know if I have other code running. Node JS, find even, identify find even has already been declared. Oh, this is cool. So we have our output, correct? 1 and 2, 1 and 3, 1 and 2, 1 and 3, 2 and 1, 2 and 3, 3 and 1, 3 and 2. Okay. Does this code make sense? For each element in the array, we pair it with every other element, skipping itself. So in the chat here, type in the time complexity for this algorithm and don't hit enter until I count 3. And give me a thumbs up once you have it, once you're ready to go. Time complexity. Thank you, Suzette, Brianne, Kathy, Douglas, Jonathan, Giselle, Sergio, Joanne, Khadija. You're the last one. Cool. Okay. The zoo. The count of 3. You hit enter. 1, 2, 3. Okay. IDK quadratic. That's a new time complexity. That's, I know what IDK means, just in case you're wondering. And I don't know a lot of slang in English. But cool, yeah, this is quadratic. Some people said, Jonathan, you said linear. Sergio, another way of saying is n squared. Yeah, n squared quadratic of n, like Douglas wrote it as well. Quadratic, cool. Yes, this is definitely quadratic. And does anyone want to attempt to explain why is it quadratic? Even though I kind of already said it, but yeah, I would like to hear it from you. Even if you say exactly the same thing that I said. Why is it quadratic? Quadratic in terms of time. Lewis?
I believe that the short answer is that it's a nested loop.
That's the short answer, but yeah, explain a little bit more.
It's because it needs to run the entire length times the entire length.
Yeah.
I think that's roughly because it's yeah.
That's a valid one. Yeah. It's because for each element in the array, it has to loop again over all elements in the array, basically, which is the same thing as another way of saying that could be, well, yeah, for each element in the array, which is n, hey, where is that? For each element in the array, we have to loop another n times. So we do, I guess somebody could have written this, and it will also be correct. N times n. How would you say of n squared? Okay. Now, same drill. Put in the chat the space complexity you think this is using, and don't submit yet. Give me a thumbs up. If you don't know, just guess. Talk about it. Okay, on the count of 3, 1, 2, 3. Okay, okay. I see some variation. That's good. Variation is good. We see of N, Jonathan and Joanne, linear, which is the same as of N, Sergio Briani of N, Douglas of N factorial, that one's interesting. And then it's linear of N, um, Suzette of N. Um, unfortunate to to say that none of you got it. But let's talk about it. That's the point. So we talked about the time. Let's think about again sort of the worst and best scenarios. Um, if we have, what is the simplest and best scenario input for this example? In terms of space, let's talk about the space. Yeah, in terms of space, what is the best or simplest case? Douglas.
Oh no, they've got to be pairs. So I guess it would be 2. It would be much like the first input, an array of 2 elements that are unique.
Okay.
That yields an output of 2 arrays.
Mm-hmm. Suzette, do you want anything to add? Or any comment?
No, never mind.
Cool. Actually, one thing that I should have said is, O of N is not wrong. It is if you define N, you could say O of N, but if you define N, it's all about like the definition of N, and we're gonna see that. So we see that for 2 numbers, we end up with 2 pairs. For 3 numbers, we end up with how many pairs? 5 pairs? No, is it 5? 6 pairs. I guess I have a pair missing here in my own. If we have 4 numbers, how many pairs would we end up with?
Is it 16?
16, or really close to 16. Yeah, is 4 times 4. That's 16. That's correct. And very close to 16. It's not exactly 16 because it's 16 minus n, or is because we're not pairing it itself with itself, each number with itself. So we will end up with n less pairings. But basically, the space complexity of this algorithm is the same as the time complexity. It's O of N squared. We will end up with, so we're, in terms of space, we start with this empty array, and this empty array will be filled with pairs of numbers, right? We'll end up with as many pairs. Let me see how I can say this. The space these algorithms will grow in a quadratic fashion with regards to the size of the input. Now I said that O of N, you could say O of N, and O of N will be correct if you say O of N where N is the number of possible pairs, right? Now the number of possible pairs just happens to be quadratic, because for each number we have to pair it with every other number, and so on. And so therefore, the space that this algorithm is going to take, if we have 4, it will be here. Let's try to come up with a mathematical formula. If it will be n times n minus n. Let's see if this holds up. So we have n being 2 for the first element, so that will be 2 times 2. This will give us 4 minus 2, right? N is 2. 4 minus 2, that gives us, you know, a total of 2. So that holds up for the first example. And if we do that for the second one, it should still hold. Let's do that one last. Oh, damn! I think we're right on time. Where n is 3, so we have 3 times 3, that's 9, minus 3, that gives us 6. And that was the number of pairs we ended up.
Bye, everybody.
Now then,
Night.
well, this one is like, I think I kind of feel like I don't have the right vocabulary to articulate very clearly the number that will end up with as many pairs as n times n, where n is the number of elements in the array. And we were seeing that quadratic time gets bad really quickly. So if, you know, I think, let's see. Quadratic, we just see, that's interesting. Oh, I'm trying to see if there is like a graph that I could show you. I mean, it's a graph that we are all familiar with, that it gets, the number of elements increases a little bit. It's like, you know, if we go back here, if we suddenly have, so for 3 elements, that was 6. For 4 elements, we said it was going to be 16 minus 4, so that's 12. For 5 elements, that will be 25 minus 5, 20. And we can see that this is starting, we're only adding 1 element. This was for 4. And the space that is taking up is almost doubling. You can see it from 6 to 10 to 12, 12 to 20. We add 1 more, that's 36, minus 6. Wait, 6 times 6, 36, is that correct? I never really learned the multiplication tables. Yeah. Minus 6, then that's 30, and so on. It just keeps going. Okay. The last thing that I wanted to show you, I guess, like, was the recursive scenario, which is one that we saw in the review that we did of recursion. Sort of talk about space complexity in terms of the recursion. We have this example, this recursive sum. I'll take a minute to read it. Also, like, I guess, read the example. Read the example here. Okay, so let me explain really quickly what this. So this function just adds the numbers 0 to n. So if we pass in, I'm just gonna call it like maybe rs. Rs for recursive sum of 5. This should give us 15 because it's 5 plus 4 plus 3 plus 2 plus 1. If we add all those numbers, we get 15. Okay, and then the way that it works is the way in which I like to visualize the recursive function going on here is we call rs of 5, rs for recursive sum, and n is 5, is not 0, so we don't go here. We go in the recursive call. The recursive call, what it's doing is, the computer sees the recursive call and it says, well, I have to return n plus the recursive calls, but I don't know what this is yet. So I need to go execute that. This is the computer speaking. So the way that I would like to visualize that is basically recursive. So the result of this will be equal to 5 or n plus rs of n minus 1, which is 4. The computer doesn't know what rs minus 4, rs of 4 is. It has to go compute that. N is 4, n is not 0, so it keeps going deeper. It goes 4 plus the recursive sum of n minus 1, which is 3. The recursive sum of 3 is 3 plus the recursive sum of 2. The recursive sum of 2 is 2 plus the recursive sum of 1. Actually, I could have stopped this at 1. And this is this is going too small now. 1 is equal to the recursive call 1 plus recursive call of 0. Now the recursive call of 0, we know the answer is n or 0, because now n is 0, we return n, so we return 0. Then at this point, the recursion stops. And now suddenly the computer knows their answer to this, which is 1 plus 0. That is 1. So then he knows their answer to this. The answer to this is 1. Then he knows the answer to this. The answer to this is 2 plus 1. Then that's 3 here. Then he knows the answer to this whole thing, which is 6. So then we get that 6 there. He knows the result of this, which is 4 plus 6, 10. We get that 10 here, and then 10 plus 5, 15, the recursion finish. So in terms of time complexity, what would you say the time complexity of this is? Let's do it one more time, one last time. Put the time complexity in the chat. Don't hit enter until I count to 3. Time complexity of this. Put it in the chat. Don't hit enter until I count to 3. And give me a thumbs up once you have it. Okay, I see some thumbs up. Cool, let's go. 1, 2, 3. Okay, so we got some variations. We got, oops. I don't want to clear the drawings. Let me just go back to my mouse. We have of n, we have quadratic, of n square, linear. So the answer is, with the majority, is linear time. I remember this also being sort of like tricky a little bit when my input is not an array, or when my input is not a string, when my input is not a list. How do I think about, like, the length? We were saying a lot of times I say the length of the input or the size of the input. Here is sort of the size of this number, how big this number is. Well, we can see that if we go back to time complexity as is also the number of operations we executed. How many operations did we execute here? N, where n is the number, and we literally call it n. We end up having one operation, 1, 2, 3, 4, 5. So the number of operations is 5, which is n. That gives us n in terms of number of operations in terms of time. And that will grow linearly. If n is double, then that will be double. If n is 1,000, it will be 1,000 of operations. Okay, so time complexity, linear, O of n. How about space complexity? This one here is tricky. I don't think we have talked about space complexity. Maybe, yeah, I don't think we have talked about it. So same thing. put in the space complexity that you think this algorithm is using in the chat. Don't hit enter until I count to 3. If you don't know, just guess whatever wild guess you want to put in. And let's talk about it to go home and to our extended weekend. Give me a thumbs up once you have the space complexity. And Sergio is hitting enter always before I say 1, 2, 3. Cool. Let's go with the people that we have. 1, 2, 3. Cool. So we got n linear constant, extra spacey constant, linear constant. So the answer is linear. And why this is sort of tricky is like we don't see any variable growing with the size of the input. We don't see any array expanding. We don't see any object growing in any fashion. So it is not constant because there is something growing. And what's growing is the call stack, basically. The call stack is occupying space in memory. We could think of it as the call stack. And the first call that gets in the call stack is when we call rs with 5. And the computer doesn't know what the rs of 5 is because it has to compute the recursive call. So rs of 5 will put in rs of 4. Rs of 4 will put in the call stack rs of 3, rs of 2, rs of 1, rs of 0. Where this puts this one in, this one puts that one in, and so on. So our stack, and it's literally like a stack like the ones you have implemented. Our call stack will be as tall as big the number is. So if we have if we pass in n 1,000, our stack will be 1,000. If we pass a long enough number, we're gonna get a stack overflow because Node has a limit on how many stuff you put on the stack. I don't know what that limit is, but it's a big number. So this stack is growing linearly with respect of the size of the input with respect to n here. So in terms of space complexity, this is linear. The stack is growing with each recursive call. That is true for all recursive algorithms. All recursive algorithms will put stuff in the stack. That stuff that's being put in the stack is occupying space. Not all recursive algorithms are of n, of course, but if they're putting stuff on the stack, they will have a space complexity. And all the recursive algorithms put stuff on the stack. One last thought or question is, so we saw that this is in terms of time complexity is O of n. In terms of space complexity is O of n. How does that compare with just doing the exact same operation, but on an iterative sum, basically with a loop? What will be the time and what will be the space? If we sum the numbers from 0 to n with a for loop, what's the time complexity of that and what's the space complexity of that? Any wild guesses?
Is it O of n time complexity and O of 1 space complexity?
Bingo, because Giselle nailed it. We are all going home right now. Yeah, that's correct. O of 1 space complexity because we're not using, there's not stuff being put on the stack. There's no variables growing with the size of the input. Cool. Any final questions or thoughts? Okay, I hope this was helpful, reviewing some of the time and space complexity. I hope you enjoy your weekend. One weekend in a very long time, that deserves some recognition. Yeah, I'll see you all Let me think. Monday?
No.
When? I don't know. I'll have to check the calendar. Cool. Have a good night, everyone.
Right.
Wait, do we not meet again until Monday for real? I'm confused by the no.
No, we definitely meet on next Monday.
Okay.
I was joking, guys. Sorry.
No, scared me.
No.
Everyone, enjoy your weekend.
You guys. Good
Have a
night.
good one, everybody.
Good night.
Night.
Bye. Have a good weekend.